In this lecture, we will continue our discussion on magnetic ceramics material. In an earlier lecture, we have already discussed the basics of magnetism, the origin of magnetism particularly in atoms due to the orbital movement of the electrons, also the spin movement of the electrons. So, we had seen there are two basic origins or basic nature of the magnetic moment in an atom. One is orbital, another is spin, and we have also seen the phenomenological magnetic behavior of different materials, and based on that we have grouped the different materials or the whole gamut of materials in 4 or 5 different groups: diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic. So, these are basically 5 different groups, and we have also seen how they respond to the external magnetic field. Some of them very weakly responds quite weakly, the other very strongly, and their origin of this response are also little different. So, we have seen up to the ferromagnetic behavior, ferrimagnetic behavior is also there. Now, ferromagnetism basically arises from the unfilled D cells, and one can find out what kind of behavior is expected from what different kind of elements having unfilled D cells. So, that is one of our first discussion in this lecture, and therefore, we first look at the so called electronic structures which we have learned in the school chemistry. What is the distribution of the different electrons in the different elements, particularly the transition metal elements having unfilled D cells. To start with, the scandium, which is the atomic number is 21, and this is how they are distributed, and one can see the first one has to see in the last 2 columns. These are all 4s2, and one can see the D1 keeping D can have over total number of 10 electrons. So, before D is filled up, the S has been filled up, and that is why it is called the unfilled D cells or D electrons, D elements. So, in all these cases, particularly this group, we can see 4 S is already filled up, whereas D is slowly getting filled up from scandium to nickel. So, scandium has 21 electrons, and this is 22, 23, 24. Iron has 26, cobalt 27, and nickel 28. One can remember that iron, cobalt, nickel are one of the strongest ferromagnetic materials, whereas copper and zinc once again is a filled D cell, but unfilled S cell. Yeah. So, this is the distribution of the electron between D and S cell. So, that is one of the major source, or that is one of the causes of strong magnetism in some of these ions. Now, with this background, we would also like to look at some other principle. This is called the calculation of saturation magnetization in ferromagnetic elements, and that is Hund's rule. Some of these ions do give rise to ferromagnetism, and we have seen the D cell is slowly filled up from 1 electron here to nickel, which is about 8 electrons. Okay. But what is the spin? Because we have also mentioned earlier that in all these cells, unfilled D cells, it is the spin magnetic moments which dominates. The contribution of the orbital magnetic moment is almost negligible. So, we are not so much concerned about the orbital magnetic moment in these cases. Our main concern is how the spin magnetic moment is behaving and how much it is contribution to the overall magnetism. So, here you have only one electron in the D cell, then in titanium there are 2 electrons, and vanadium 23 has 3 electrons, chromium have 4, manganese has 5, and then iron has 6, and so on. So, one thing you have to notice, that is what we call the Hund's rule, how the spin is getting arranged. There are 2 different spins, half plus up and minus up. So, the first electron will have plus up and the second must have the minus up, that is the normal expectation. However, in this case that is really not so, and that is given, or that is the rule of Hund's. First of all the electrons still all they fell, because you have 5 subcells, each subcell has can accommodate 2 electrons of 2 different spins. So, if the second electron comes or is present there in titanium for example, the spin will be the same as that of the first. Okay. So, it is not this electron will fill up the first subcell first and then the additional electrons will go to the next subcell. It is not so. So, till all the 5 subcells, 10 electrons have been subdivided or grouped under 2 each. So, you have 5 subcells, and then all the 5 subcells must be filled up with electrons of the same spin. So, this is if this is positive, these 2 also will have positive, the third electron will also have positive spin, and fourth electron and so on till the 5th electron is added. 5th electron is in the manganese. So, manganese have 5 D5 and all the 5 will be filled up first, the same spin, and 6th electron will fill up with a reverse spin. So, in iron for example, the 6th electron D6, this will have the same spin, okay, sorry, the different spin as in the first one, and so on. So, the 7th one will have in the second cell, and third one will be in the third cell. So, this will have one kind of orbital moment, the spin magnetic moment. This will also have same spin magnetic moment in the same direction. So, up to the 5th, up to D5, the magnetic moment will increase, and each magnetic moment, if you remember our discussion earlier, each electron will give rise to 1 Bohr magneton. Okay. This gives you 1 Bohr magneton, this is another 2 Bohr magneton, and 3 Bohr magneton, 4 and 5 and so on. However, when we add 6th one, then this will have a positive spin and this will have a negative spin, and they will cancel each other. So, the resultant will be 4 Bohr magnet. So, up to this the number of number of electrons will increase with the same spin, and therefore, the magnetic moment will also increase, and after that this will decrease. This will decrease. So, D6 will have only 4 resultant Bohr magneton, D7 will have 3, and D8 will have only 2, right. There is no D9, it will be after that, after nickel actually it becomes D10, both copper and manganese, as you have seen earlier, both copper and manganese actually D10. So, there is no D9 here, okay, because up to this this is 4s2, and then once again it becomes 4s1. So, D10 and 4s2 D10. Okay. So, these are basically supposed to be diamagnetic without any resultant magnetic moment. So, this is what we call the Hund's law, how the additional electrons are getting filled up or providing having in which particular subcell it is going, and initially all the 5 till the 5 d electrons, all the 5 will have the same spin, then the reversal will take place, okay, one after the other. So, this is an important concept and important criteria one must remember. Now, in addition to the element, this is scandium 21, titanium 22 electrons, we have vanadium 23. Now, there are few other ions are also mentioned, and the number of electrons are actually 21. If you go back to the earlier table, chromium actually has 24, and if you have chromium 3 plus, that means 3 electrons have been donated, have been removed. So, it becomes actually 24 minus 3, it becomes 21 electrons, and this 21 electrons, sorry, not this one, previous one, 23 electrons chromium has also 21 electron, 3 has been removed from here, and these 3 are actually this 2 and this one. So, it becomes D3, it becomes D3, that is why it is mentioned here, it is 21 electrons, but it is a D3. So, this is actually 3 D3 D electrons are there. Similarly, the case with manganese 4 plus, manganese is actually 25, here it is 25, you can see, okay. The element has a 25 electrons, whereas 4 plus have 21 electrons, and out in which you have 3 D electrons, okay. So, it is a 3D structure, and that is similarly here chromium, the elemental chromium has 24 and it is a D4 configuration, whereas Mn3 plus, okay, Mn3 plus is also D4 configuration, although it has only 22 electrons. Manganese basically 25 and 3 electrons are removed, so it becomes 22. Whereas, if it is manganese 2 plus, then it is 23, 22, 25 minus 2, 20, 23, and that is also have the same configuration of D5. Fe3 plus is 23 electrons, as such Fe is 26. So, if you remove 3 electrons becomes Fe3 plus, and it becomes again a D5 configuration, and that is how few more ions have been mentioned. Fe2 plus also have the same, elemental Fe and Fe2 plus have the same configuration of D6, that is clear from here. This is D6. So, Fe2 plus will, these 2 electrons will be will go away, so it will be D6. So, whereas copper 29 and zinc 30 completely filled cells, whereas nickel 28 has D2, it is D8, and this nickel 2 plus also same configuration. So, far as the D cell is concerned, number of electrons will be different because S electrons are actually getting removed, but the D cell configuration remains unchanged. So, this is a very important consideration when you are discussing about the magnetic moment of D cell electrons, D cell atoms, unfilled D cell atoms. Here is a list based on that. Here is a list of magnetic moments of isolated 3D electron elements or ions. Depending on the number of electrons available in the D cell, these are some of the ions. Scandium 3 plus is 3D is a D0 configuration, so there is no magnetic moment. Orbital magnetic moment, as I mentioned, is not playing any role in this. It is only the spin magnetic moment which is important. So, it is the number of electrons in the D cell which is of our concern. Vanadium 4 and titanium 3 is 3D1 and calculated moment, magnetic moment is 1.73 by the formula which you have shown earlier, that mu b into S into S minus 1. If you do that, that gives you this kind of a 1.73 is the calculated value, and the resultant and the experimental value is very close to that. Okay. So, it is 1.80. Similarly, vanadium 3 plus is a 3D2 configuration, 2.83 is the calculated and the theoretical is 2.8. It is very good agreement. V2 plus and chromium 3 plus is a D3 configuration. So, it is 3.87 and 3.80. This is the theoretically calculated value, and the actual measurement is 3.8. Manganese 3 plus and chromium 2 plus is D4 configuration and 4.90 Bohr magnet. Remember, these are 4.90 Bohr magnet, mu b multiplied, the actual value will be multiplied by the value of mu b. So, 4.9 multiplied by mu b. Similarly, it is exactly same, 4.9 multiplied by mu b. Mn2 plus and Fe3 plus 3D5, this is configuration, this is 5.92 and 5.9. Iron 3 plus, iron 2 plus, okay, iron 2 plus is 3D6, 4.9. Now, 4.9 and 5.0, there is a slight difference here, okay. It is not exactly same. So, the reason of course is different, not from here, but is not too different. Okay. Cobalt 2 plus 3.87, 4.8, again once again beyond this the difference or the matching is not that well, but above this the matching is quite well. Okay. So, it depends on the total number of electrons here. Beyond 3D5 the matching is not that good, for example 2.83 and 3.2, copper 2 plus 3D9 and copper plus as well as zinc 2 plus is 3D10. So, 0 0, this is certainly quite expected, and that is what we get in the measurement, experimental measurement also. So, this is not a ferromagnetic material, neither this is a ferromagnetic material, but some of these tangent metal oxides do contribute to the ferromagnetic oxide, of course not when, because most of them are ions, and so their contribution comes in when in the form of oxides, and that we will see in the form of ferrimagnetic materials. Well, to continue our discussion on ferromagnetic materials, we have seen that these three elements, iron, cobalt and nickel, are the strong ferromagnetic materials, okay. Whereas the other element in the transition metal series, although they have a unfilled D cell and they have their individual magnetic moments of each of the atoms, but the overall magnetic moment in the form of a solid in the crystal, it is not that strong, and that comes from the consideration of what we call the exchange energy term. It is the exchange energy to explain magnetic ordering of, this is called the Bethe-Slater interaction. So, it is the interaction between the atoms within a particular crystal structure, depending on the d cell diameter of the d cell, that means the number of the d cell electrons and their arrangement, and also the interatomic spacing between the two atoms. So, these are the two different parameters which has a very important role in actually providing the magnetic behavior, to explain the magnetic behavior of some of these elements, not the oxides. Oxide will consider later. So, it is exchange energy term which is WW, without going to the details of that. This is an important important plot from this Bethe-Slater interaction, and that very well explains why some of the unfilled d cell electron or d cell elements have a strong magnetic interaction or very strong magnetic moment, whereas the others do not. So, once we plot this exchange interaction energy or exchange energy against this ratio, the ratio is AA by R3D. AA is nothing but the ratio of the interatomic distance. A is the interatomic distance of that particular crystal structure, in that particular crystal structure, and then the radius of the 3D cell. Obviously, the radius of the 3D cell depends on the number of electrons available in the cell, and their interaction with each other. So, if you plot that, you will find these three elements, alpha iron, cobalt and nickel, they have a very positive interaction energy or positive exchange energy. So, WW, when it is positive, there is a strong ferromagnetic ordering. We will see what is exactly a ferromagnetic ordering, but individual atoms may have magnetic moments, but when they are combined in the form of a crystal structure or crystal, the ordering may vary. That means some of them are more disordered than the others, and more order means more resultant magnetic moment. So, that is what we get when exchange energy is positive. There is a ferromagnetic ordering, that means all the atoms with a particular spin and with a particular resultant magnetic moment gets aligned in a particular direction and in a parallel way, and therefore, you have a strong coupling, there is strong magnetic effect. If it is negative, for example, manganese and chromium, although they have unfilled cells, d electrons, but even then, because of the exchange interaction is negative, there is an anti-ferromagnetic ordering is prevailing. Okay. So, if it is less than 0, there is anti-ferromagnetic ordering, and which neutralizes each other, and therefore, the overall magnetic moment is almost nil. Here is some, if it is very close to 0, WW equal to 0, small, and this kind of material is basically paramagnetic. So, if it is fairly lower than 0 like this, they have a antiparallel ordering. If it is close to 0, then it is paramagnetism, there is a random ordering, and then if it is more positive, then you have a ferromagnetic ordering or parallel ordering, parallel alignment. This is antiparallel alignment, this is random, and then this is parallel element. We will see this little more clearly later on. So, ferromagnetism means a very strong magnetization, and they respond to the external magnetic field very intensely, and they have a permanent, some kind of a spontaneous polarization, spontaneous magnetized polarization. However, this spontaneous magnetized polarization, what we call the saturation magnetization here, is very strongly temperature dependent according to the Curie-Weiss law, the Curie law. Okay. And this relationship, this is the temperature dependence, basically the temperature dependence of ferromagnetism, because all magnetism, all magnetic behavior has some temperature dependence, because higher is the temperature, higher is the thermal energy or thermal vibration, more is the disorder. So, even at a lower temperature, if you have a strong parallel orientation or anti-parallel orientation or less magnetic moment. So, all of them have some temperature dependence. We have seen earlier that the paramagnetic, in case of paramagnetic there is a inverse law which determines the temperature dependence. Here it is also a kind of inverse law, but with a slight difference. Earlier in case of paramagnetic property or paramagnetic materials, the chi m, the susceptibility was C by T, that was the relationship. Here it is more or less same, but with slight difference, there is a critical temperature T c. So, the critical temperature is the temperature where it becomes nil, the magnetic saturation or magnetization curve ultimately drops off. So, at T equal to T 0, chi m becomes very high, okay, almost infinity. But otherwise, if you plot the magnetization, that is the saturation maximum magnetization available from the material as a function of temperature, we will see at room temperature, close to room temperature, it does not vary so much, more or less remains constant, and then as the critical temperature is reached, there is a, this is the critical temperature, the T c. As the critical temperature is, the polarization or the magnetization drops off quite suddenly, quite sharply. So, for nickel, these are the three important ferromagnetic materials. One can see there is a critical temperature in each case. This temperature is slightly higher than 1000 K, this is about 1400 K, and this is around 650 K. Okay. So, nickel has a low Curie temperature, this T c is called the critical temperature or sometimes also referred to as Curie temperature. So, each ferromagnetic material has a characteristic temperature beyond which the ferromagnetism is lost. So, beyond that, because of the thermal vibration, there is no magnetic ordering and the atoms get disordered so far as the magnetic lines of magnetic moment is concerned. So, cobalt has the highest Curie temperature about 1400 K, then iron is around 1050, and this is about 650, okay, 650 K. So, at lower temperature it is more or less constant, and that is the reason it is called saturation magnetization. This is polarization versus by temperature. Okay. So, this is the relationship of ferromagnetism against temperature. This is what I was talking about, the magnetic ordering. We have seen there is a magnetic moment originating from either from the orbital magnetic moment, orbital phenomena or the spin phenomena, but for our purpose orbital phenomena is not that much of importance, spin phenomena is more important, and that is the major contributor to the magnetic moment, overall magnetic moment or macroscopic magnetic moment of the material. But well, those spin magnetic moment are actually not the macroscopic, but it is more of an atomistic. Each atom is contributing to the overall magnetic moment from its spin situation. Now, in case of ferromagnetic, this is a what we call a ferromagnetic ordering, this is ferrimagnetic ordering, and this is antiferromagnetic ordering. In ferromagnetic ordering, each of the atoms or each of the magnetic moment is aligned in such a way they are in parallel orientation. Okay. We will look into this what exactly it means, but there is a parallel, all the magnetic moment are parallelly oriented, that means they are pointing out in the same pointing to the same direction, and therefore an additive effect, there is an additive effect. So, all of them actually combine to give you the macroscopic property. So, therefore, that is the reason why it becomes more strong, it has a strong magnetic moment, the overall magnetic moment, resultant magnetic moment is very strong or very high, and that is the reason the chi is also more than 1, and permeability is also very high. Permeability is certainly because of this reason. If you have a antiferromagnetic ordering, the last one in this case, you will see it is the same thing, but each one has an opposite spin or each one has an opposite magnetic moment in their aligned in the opposite direction, and therefore, there is a cancellation. The overall magnetic moment of the assembly becomes very close to 0, and therefore, it more or less, so far as the permeability is concerned, is more or less like a paramagnetic material. So, it is although individual element, individual atoms has a strong magnetic moment, but the overall resultant magnetic moment is almost 0, very close to 0, and that is why this antiferromagnetic property or antiferromagnetic materials are grouped with along with the paramagnetic materials. They also have the same thing, but for a different reason. They are because of the more random nature or less magnetic moment for individual atoms. Whereas, there is a ferrimagnetic ordering, there is another ordering which is mostly present in oxides, not in elements. This is also incidentally, this is also in oxides, primarily occurs in insulators and oxide insulators. This occurs primarily in metals, and there is requires free electrons in the conduction band. Okay. So, that is another requirement which gives rise to the strong parallel alignment. Now, in the ferrimagnetism is also antiparallel, very close to antiferromagnetism, but in the two directions they are unequal, the magnitudes are unequal, although their alignments are antiparallel like antiferromagnetism, but the magnitudes are different, and therefore, there is a resultant magnetic moment. So, the downward directions are smaller, whereas the upward alignments or upward oriented magnetic moments are larger, and therefore, there is a positive resultant positive magnetic moment in a particular direction. So, like this, like ferromagnetism, they are also strongly coupled, they can be strongly coupled with the external magnetic field, but unlike this antiferromagnetism where they can be only weakly coupled. So, these are the three different kind of orderings available in different materials. This requires, as I just mentioned, requires free electrons in the conduction band, so mostly available in metals. they are primarily insulators, and these two groups are primarily oxides. So, when we talk about magnetic ceramics, we are talking about basically these two groups of material, okay, either ferromagnetic or antiferromagnetic. So, far the temperature dependence is concerned, both these ferromagnetic, because they are strongly coupled and they have some kind of a critical temperature, which is the Curie temperature, and this is available both ferromagnetic. We have seen the example of ferromagnetism or ferromagnetic materials, how this temperature dependent, the saturation magnetization becomes nil at above a temperature because of the thermal vibration. They become no longer becomes parallel orientation, parallel alignment, they becomes randomly oriented, and therefore we lose the magnetic property. Whereas here in case of antiferromagnetic ordering, which is they have a critical temperature, they are also has a critical temperature which is called nil temperature, okay, Tn, and that happens below the critical temperature Dn. So, again beyond that temperature this alignment is no longer there. So, you get a random orientation and you may end up with a paramagnetic material. So, both of them, all the materials change over to a paramagnetic behavior beyond a certain temperature. This is a very important phenomena of ferromagnetic and ferrimagnetic materials. So, the characteristic hysteresis curves, if we plot, we have seen earlier for the paramagnetic and diamagnetic, there is a linear magnetic material. That means, if you plot the magnetic induction or the magnetic polarization against H, you end up with a linear relationship. Here, particularly for these two groups of magnetic material, whether it is ferromagnetic or ferrimagnetic, they have identical properties so far as the external magnetic field is concerned. So, when you apply an external magnetic field, let us start from here, it has a nonlinear characteristics. Okay, it has a nonlinear characteristics like this. It goes to a saturation value, a highest value where it saturates, the magnetic induction or the polarization gets saturated at some value of external magnetic field. But then if you reduce, if one reduces the magnetic field or reverses the magnetic field, it follows a different curve or different path. So, initially from 0 field it follows this red line and then goes to the blue line, and it follows a different path altogether. And even at 0 field, when in the reverse direction, when the field is 0, you have a value of the magnetic induction or polarization. So, the material is still magnetized, and you have a remnant magnetization, remnant flux density, one can say remnant magnetization or remnant flux density. This is Br. So, it does not come back to 0, it does not follow the original path, and then you need a additional negative bias or negative field in the opposite direction. You have to apply a field in the opposite direction to bring that value to the 0 value, and this value of the magnetic field, which is needed to neutralize the remnant flux density, is called coercive field. These are all the terminologies which has also been used for ferroelectric material. In fact, The ferroelectric have been discovered much later than the ferromagnetic group of materials. So, ferromagnetism was known much earlier, but we have discussed in a reverse way. So, in our discussion ferromagnetism comes later than ferroelectricity, and that is why I am referring to the earlier discussion of ferroelectricity. So, the origin is same, the reasons of this kind of hysteresis loop or hysteresis curve are exactly same, and it follows the similar pattern, and also terminologies are also very similar. In the case you have remnant polarization there, here that was electric polarization, here magnetic polarization, coercive field in dielectric material it was electric field, here is a magnetic field. So, otherwise it is same. And as you have discussed in case of dielectric material, it is basically this kind of a hysteresis curve or the origin of the coercive field or the origin of the remnant field, remnant flux density, remnant polarization is primarily because they have a domain structure. Okay. We will see in a minute what is the domain structure. So, that domain structure changes from 0 field to higher field, okay. And this is to some extent much sluggish in nature. This movement is much sluggish, this changeover is much sluggish than the rate of change of the magnetic field, and therefore, it has a memory effect. So, it changes from a more or less random structure, random domain alignment to almost a fully aligned domains, and that has its own relaxation time. So, it takes time, and therefore, immediately it does not come back, to the randomness. So, the alignment, preferred alignment is exists even after the withdrawal of the magnetic field. So, that is the origin of the hysteresis loop or the hysteresis curve, particularly for ferroelectric and ferromagnetic and ferrimagnetic materials. This is curves for soft and hard magnetic materials. Well, when we are talking about ferromagnetic materials, there are two types of ferromagnetism. One is the soft magnetism, hard magnetism. That means in hard material it is difficult to magnetize and also difficult to demagnetize, okay. Whereas in soft magnetic material it is fairly easy, that means you need much less external field to fully magnetize it or saturate the magnetization, and also you need much less reverse magnetic field to demagnetize it. So, these are the two correct depending on the basically depending on the area of the hysteresis loop. Okay. There are two different loops, the area under the curve, because the area under the curve measures the total amount of energy needed to magnetize or demagnetize it. Okay. So, this is a much fatter or a very high energy hysteresis loop. So, the width is much larger, and also so the coercive field is large, okay. This distance is large from 0, and to magnetize it, fully magnetize it, that is also quite large. The remnant magnetization is also very large, okay, and you need more magnetic field in the reverse direction to neutralize it. So, the total overall shape is a large hysteresis loop. So, if there is a large hysteresis loop, this is as I mentioned, it is difficult to magnetize and also difficult to demagnetize. That is why there is a possibility that it retains its magnetization after the external field is withdrawn. So, it can get converted to a permanent magnet. So, such type of material will be can be used as a permanent magnet, whereas these are soft magnetic materials, they cannot be used as a permanent magnet. The magnetizing will be lost with very little of demagnetizing force, and therefore, they can be used as more of an electromagnets, where the magnetic field will vary with the application of the external magnetic or the magnetic moment or magnetic polarization, magnetic induction will vary almost in phase with the applied magnetic field. So, that has its own application, particularly in many of the electronic devices, including the memory for computers, but these days of course these kind of memories are not used, but it can be used for miniaturized transformer cores, spot cores and so on. We will come to that later. So, both these varieties of magnetic materials have their own usefulness, and one can design different devices based on this particular characteristics of whether it has a large hysteresis loop or a small hysteresis loop. Well, this is an example. We are talking about the antiferromagnetic material, and this is an example of antiferromagnetism. It was also mentioned that some of the oxides do have this property, and this is an example of manganese oxide MnO, which is having a sodium chloride structure, and these are these positions of the manganese and oxygen ions. These are a cubic symmetry, closed packed cubic symmetry. So, these large ions are the oxygen ions, and the corner ions here are the manganese ions, manganese 2 plus. So, these are the manganese 2 plus ions along the diagonal here, and on the edges or on the center of the edges we have oxygen ions. Of course, it can be it can be reversed also, reversed in the sense it can be drawn. Basically, it is the same distribution, but the unit cell can be drawn either with the cation at the cube edges, corners, or oxygen at the cube corners. Both the systems are equivalent basically. So, these are the manganese ions and these are the oxygen ions. Using the so called Hund's rule, we can find that each manganese ion has a positive magnetic or strong magnetic moment. Okay. Each manganese ion has a strong positive magnetic moment, and therefore, they all have certain amount of magnetic moments of the ions. Now, some of them in between the two cations will always have some oxygen ions, and the oxygen ion is basically a diamagnetic, or there is a antiferromagnetic kind of coupling within the oxygen ion. That means this oxygen, this is the overlap of the 3d orbitals of the 2p orbitals of the oxygen ion. So, this is details of the electronic configuration. Here it is the 2p orbital, this is the oxygen ion, and this is the 2p orbital, one lobe on this side, another lobe on this side. These are the orbitals of the D cell of the manganese ion, manganese 2 plus ions. So, you have 4 orbitals, and there is always the structure is such that there is an overlap between the 3d orbitals of the Mn2 plus and 2p orbitals of the Mn of the oxygen 2 minus, gives rise to antiparallel alignment. Well, we are not going to the details why exactly it happens, but this much information is acceptable, I mean okay for our purpose, that this overlapping of the orbitals gives rise to the antiparallel alignment of the neighboring Mn2 plus ions. This is Mn2 plus ion, one Mn2 plus ion here and another Mn2 plus here, we have oxygen in between. So, because of this overlap, this is directed in this particular direction towards front, whereas this towards back. Okay. So, the next one, all this particular set of Mn ions, Mn2 plus ions are all directed, alternate ones are directed to the different directions. Okay. So, these are actually d4 electrons, and these are there is a exchange of electrons here. Okay. So, this Mn2 plus and this Mn2 plus are directed in 2 different directions. This is the basic reason, and because of this you have a antiparallel orientation, and it is called the antiferromagnetic materials, although the individual cations have a strong magnetic moment. The same is the case with other rock salt structure oxides like FeO, cobalt oxide and so on, nickel oxide. The antiferromagnetic materials also have, they are strongly magnetic material, but sorry, they are weakly magnetic material, they are weakly magnetic material, and they behave some kind of a paramagnetic way. This is another picture, giving rise to the orientation. As you can see, if you look at this layer of atoms, each one of them neighboring ions have a different orientation. These are of course oxygen ions, these are again manganese ions oriented in opposite directions and so on. And there is a temperature called nil temperature. Antiferromagnetic ordering takes place at a temperature below the nil temperature here. This is the nil temperature, and the ordering is lost due to thermal vibration at temperature greater than Tn. So, very similar to Tc in case of in ferromagnetic material, the Curie temperature you have a nil temperature, and then the ordering can be, or the temperature dependence can be expressed in this manner, C by T minus theta. Theta of course is this one. Sometimes it is also written as T plus Tc, where Tc is the negative value and it is called the Tn. Okay. So, this is the Curie-Weiss law with negative Curie temperature, it is called negative Curie temperature, that is this one. Okay. But if you take Tn, it becomes T plus Tn. So, that is the characteristics of the antiferromagnetic oxides, particularly the oxides with rock salt structure. Well, we complete this discussion here, because next discussion will be on a separate group of materials, that is called ferrimagnetic materials, which are actually the most important group of magnetic ceramic materials, and they have enormous application potentiality. And just to give you an idea that these are ferrimagnetic materials, once again oxides, and they have a particular crystal structure. In fact, we will see later on there are 3 particular structures in which these oxides crystallize, and they are all very strong magnetic materials having very similar characteristics as that of ferromagnetic characteristics. Although as I mentioned earlier, their origin is different and their coupling between the atoms are quite different than that of ferromagnetic materials. Ferromagnetic materials appear only on elements like transition metals, iron, cobalt, nickel and their alloys, whereas a large group of oxides do have the ferrimagnetic ordering, and they are also strongly magnetic materials with tremendous application potentiality. We will discuss further about these materials in greater details in the next class. Thank you for your attention.